All right, let's just jump right in. We're about to tackle one of the most profound and frankly unsettling mysteries in all of science. It's a puzzle that really makes you question what reality even means, and it all boils down to a single, almost childishly simple question.
No, really, think about that. How? This isn't some sci-fi plot. It's a real question that has baffled the most brilliant minds on the planet. It's as if the fundamental building blocks of our universe have a serious case of stage fright. They act one way when no one's looking, and completely differently the moment we try to sneak a peek. To even begin to understand this, we need to go back in time, to a truly legendary experiment.
It's called the double-slit experiment. And trust me, pretty much all the mind-bending weirdness of quantum mechanics can be traced right back to this one setup. It starts with a really simple comparison between things we get and things we, well, thought we got.
So, picture this. If you take a machine gun and you fire it at a wall with two vertical slits in it, what do you expect to see on the wall behind it? Two lines of bullet holes, right? Simple, makes perfect sense. But now imagine sending water waves toward those same two slits. You don't get two distinct lines. You get this beautiful, complex pattern of many lines where the waves have messed with each other. Yeah, this is what we call interference. As the two new little waves spread out from the slits, they start to overlap. Where the peak of one wave meets the peak of another, you get a bigger wave. But where a peak meets a trough, poof, they cancel each other out completely. And what you're left with is this classic signature of a wave, a whole series of alternating bands, not just two.
And that is precisely what a scientist named Thomas Young saw way back in 1801. He shone light through two slits and got that perfect interference pattern. So for about a century, that was that. Case closed. Light is a wave. But then, the quantum world showed up, and the story got a whole lot stranger.
Okay, so this is the part where our comfortable, everyday understanding of the world just kind of goes out the window. Physicists started wondering, hey, what would happen if we tried this experiment not with something wavy, but with actual solid particles?
But first, even the story of light itself got weird again. You see, Newton originally argued light was a particle. Then Young seemed to prove it was a wave. Then, along comes Albert Einstein in 1905, and he shows that light also acts like a particle, a little packet of energy he called a photon. So, which is it? Well, somehow it's both. This was the birth of this crazy idea called wave-particle duality. So, with that paradox rattling around, scientists in 1961 decided, let's run the double-slit experiment with electrons. Now, electrons are not waves. They're tiny little bits of matter. They have mass. For all we know, they're like microscopic bullets. So the expectation was crystal clear. We're going to see two simple lines on the detector. But that is not what they found. Not even close.
They got an interference pattern. Just let that sink in for a minute. These solid individual particles, when you fired them through two slits, were behaving like waves. They were creating that signature pattern with all the extra bands. It was completely baffling. But the next logical step they took made it even crazier. Now, the immediate thought was, okay, maybe the electrons are just bumping into each other in the beam and creating this weird pattern. It's a fair guess. So they said, all right, let's slow it down. Let's fire just one single electron at a time. Now, there's nothing for it to interfere with. It has to go through either the left slit or the right slit. So over time, it should just build up two lines, right? Wrong. Unbelievably, even when firing them one by one, after thousands of these single electrons hit the screen, that same exact interference pattern emerged, dot by dot by dot. This is the absolute core of the mystery. It's as if each individual electron, all by itself, passed through both slits at the same time like a wave, interacted with itself, and then landed on the screen as a single particle. It was so bizarre, they just had to try and catch it in the act.
And this is where the story turns from just strange to deeply, profoundly unsettling. The next obvious step for scientists was to figure out what in the world was actually happening at those slits. They had to watch.
So, they set up what's called a which-way experiment. They put a tiny little detector right next to the slits, a sort of microscopic bouncer whose only job was to say, yep, that one went through the left door, or, okay, that one went right. That's it. They weren't trying to change anything, they were just trying to get some information.
And the moment they did that, the interference pattern was gone, completely vanished. And what was left? Just two simple lines, exactly what you'd expect from tiny bullets. It's like the electron, knowing it was being watched, instantly dropped its weird wave act and decided to behave like a normal, respectable particle.
This phenomenon has a famous name, the observer effect. It's the idea that particles literally behave differently when you're measuring them. Now, the first guess was obvious. Maybe the detector is just physically bumping into the electron and messing it up. So physicists came up with an even more brilliant experiment to get around that.
What comes next is an experiment called the Delayed Choice Quantum Eraser, and it is honestly one of the most mind-melting ideas ever cooked up. The goal was simple: figure out which path a particle took without ever touching it. The plan relied on a spooky property of quantum mechanics called entanglement. Basically, a special crystal takes one photon and splits it into two entangled twins. These twins are linked. Whatever you learn about one, you instantly know about the other, even if they're miles apart. So twin A goes to the main screen, while twin B goes to a totally separate detector. Here's the genius part. By measuring twin B, you can figure out which path its sibling, twin A, must have taken, all without ever getting near it.
And the result? Exactly the same. As long as they had a way to know which path twin A took, even by looking at its distant twin, there was no interference pattern. Even this ghostly, hands-off kind of observation was enough to make the photon pick a side and act like a particle. But then, they added one final, jaw-dropping twist.
They added what they called erasers to the path of twin B, things that would scramble its information, making it impossible to tell which slit its sibling went through. The result is just staggering. For all the photons where the which way information was available, they acted like particles, two lines. But for the photons where that same information was erased, the interference pattern came back. This proves the most important point of all. It's not the physical act of measurement that changes things. It's the mere existence of information about the path.
So, where does that leave us? It leaves us staring into the abyss, questioning the very nature of reality itself. It suggests that, on a fundamental level, reality isn't some fixed, solid thing. It's more like a fuzzy cloud of possibilities that only snaps into a definite state when information about it exists.
This whole idea sparked a legendary debate. Albert Einstein hated it. He famously called it spooky action at a distance, and was certain there had to be some deeper hidden reality we just weren't seeing. But other physicists, like Niels Bohr and Werner Heisenberg, they basically said, nope, this weirdness is reality. And you know what? Experiment after experiment for decades has proven that Bohr and Heisenberg were right.
And look, this isn't just some abstract philosophical argument. The very technology that surrounds you is built on these exact principles. The transistors inside your computer, the lasers used in medicine, all of it only works because we've learned how to harness this bizarre quantum behavior, even if we can't fully explain why it works that way.
Which brings us to that final massive question. If an electron is just a wave of pure potential until information about it is known, what about a rock or the moon? If reality itself is only defined by what is known, what is the universe actually doing when no one and nothing is there to observe it? That is the quantum puzzle.